Hi guys, welcome to the what. So today we will see MATLAB simulations on single phase full bridge inverter using square pulses. We will generate our own square pulses. We will not use a pulse generator. We've already simulated half bridge inverter in the earlier video. Please go and check that first, so you will get a basic knowledge that how an inverter works. So let's get started. So an inverter. So an inverter is a DC to AC converter, right? So in the earlier video, you will see, or you have seen, that we were only using two of the semiconductor switches, right? And the voltage is divided into two parts, right? VD by 2 and VD by 2. The load is connected in the between of that voltage, right? So here we will not do anything like that. So here we will use one DC voltage source and four semiconductor switches, right? And load. So initially we will see the simulation on only resistive load, right? So first we will be familiar with the output waveforms, and then only we will see how it would react if a inductive load is present, right? So we already know the working of the inverter. We have seen the working in the earlier video, that is the half bridge inverter. So in the full bridge, the working is similar only. So, but here at one time, two semiconductor switches will be on, right? So let's see. So this is S1, this is S4, here this is S3, and this is S2, right? So we will trigger each of these semiconductor switches at 50 hertz, that is the power frequency available in India, and 50% duty cycle, right? So if we put 50% duty cycle, then and then only we will get positive and negative half cycle of our AC output equal, right? So we have to make sure that our output is equal and opposite, that is the same area it will cover in the positive section as well as the same area it will cover in the negative section. Then only we can call it an alternative supply, right? So at what time we will trigger them, right? So the first in IGBT or MOSFET switch as well as the fourth MOSFET switch, we will trigger simultaneously. So let's draw its waveform. Right, and the third one and the second one, we will trigger them simultaneously using a not gate pulse on them. So it will be exactly opposite to the first waveform, right? So now let's see that how the current in the load and the voltage across the load will react. So while this half cycle, first and fourth are on and third and second are off. So that means our current will start from VDC. It will come here. It will see that it has two directions, this one as well as this one. But it will not go in the third one, as third one switch is off. That means it is open circuited. So all the current will go through first semiconductor switch. Now it will come here. It will have two other options. but we can see that second switch is also off during this duration. So all the current will flow from the load. It will go from the fourth semiconductor switch and it will go to the negative side of this battery, right? So that means the load will be positive and negative, right? And current is flowing from positive to negative. So our output would be some positive cycle, right? This is the first half cycle, right? So now let's see what will happen in the second half. So in the second half, we can see that this one, first and fourth are off, and third and second are on. So what will happen? Current will start from here. It will not go in the first one as the first one is off switch. It will go in the third one. It will come down and now it will now go to the load. It will not go to the fourth switch, right? So it will go to the load. It will come down from second one, as we know second is also positive, and it will go back to battery. So at this time the load will be positive here and negative here, and current will flow in the direction accordingly, right? That means current will flow in the opposite direction. So we can say that it will come in the negative one. It will be constant for some time and this cycle will repeat, right? This is the 0, right? And the magnitude will be VDC. In the earlier video where we were doing the simulation, the magnitude was VDC by 2, right? So let's see the simulations. So these are the components that we require: DC voltage source, RLC series branch, voltage and current measurement, IGBT, sine wave generator, or a triangular wave generator. We can use both of them. Gain, constant, comparator, or a relational operator, right? Relational operator sign is something like this, right? One scope, one display, power GUI, ground block, add block, and multiplexer, right? One more thing that we will require is the logic gate. So from this logic gate, we will convert this into our NOT gate to give the same pulses but in the opposite direction to the other two semiconductor switches. So let's see how we will do the simulation. So let's check what do we need here. So first we will require a DC voltage. Take this black one, DC voltage source. Then we will be taking RLC series branch. Then voltage measurement. Current measurement. Then IGBT. Take this one. Then triangular wave generator. Take this. Then gain. Add block. Relational operator for comparison or a comparator. Logic gate. then a scope, then power GUI, display, ground, take this ground, constant, we forgot constant, one multiplexer, one, one RMS block as well, because now we will work with AC supply, so we required RMS block, that is the root mean square block, right? So I guess we have everything, so let's get started. So here also we have two main circuits. One is the triggering circuit and the other one is the main circuit, or one can be controlling circuit as well. So I'm making our controlling circuit. This is an IGBT. Let's open this, delete this measurement port. This is the current measurement, voltage measurement. This is the load, and this is the main DC supply. Right. So let's take 4 IGBTs. So let's connect them. And put ground here to stabilize the whole circuit. Convert this to R load of 10 ohms. This is the positive current direction. Here will be the voltage measurements. Right. Let's change this AND gate to NOT gate. And NOT gate will go here as well as here. The scope, let's change the scope in two input form. One will be the comparison value of these two, and the second one would be the gate pulses, right? Let's change this frequency to 50 hertz and right here minus 90 degree, because I'll explain you later why minus 90 degree. Multiply with 0.5, add 0.5, compare with 0.5. So let's see that what output we are getting. We will run for 3 power frequency cycles. Here we can see that we are getting a square wave output pulse with 50% duty cycle, and we did minus 90° in the triangular wave pulse to get this positive cycle from starting, right? So we know that whenever the triangle is more negative than the compared wave, that is the constant wave, the output will get is positive. So to get this positive output first, I started this wave from minus 90°, right? No other reason. So now connect this gate pulses here, as well as this gate will connect here. This not will also connect here, not will connect here, right? Hmm. So now let's take one more scope. So the first one would be the positive gate pulse, second one would be the not gate pulse, third one would be the output voltage, and fourth one would be the output current. So 4 waveforms are there that we need to observe, 4 different layouts, right? First one would be the positive waveform, second one is the not gate waveform, third one is the output voltage, the fourth one is the output current, right? So now we need to check the RMS value. So let's connect this here and let's set this to 100 volts. Yes, this is 10 ohm, right? Everything is set. So let's play. So here we can see we are getting 97.86, which is nearer to 100 volts. That was our input, right? So why it is not exactly 100 volts? Because these semiconductor switches have some input or some internal resistance. So due to that, some drop will occur, right? So if we observe the gate pulses, we can see that the first pulse is the positive gate. The second one is the NOT gate of the first one, so it will be exactly opposite. The third one would be the output voltage. So we can see here it will go from 100 volts, then it will go to minus 100 volts, plus 100, minus 100, so on. And according to it, we have our current. And we have taken 10 ohm resistor here and 100 volt supply, so we'll get 10 ampere current and minus 10 ampere current, right? Frequency, we can see that it is 0.02. One complete cycle takes 0.02 seconds. That means it is 50 hertz. In one complete second, it will complete 50 cycles, right? So this is the open loop operation, I must say, of a square pulse single phase full bridge inverter. So the difference in half bridge and full bridge is, in full bridge we are getting equivalent output of the input, but in half bridge we were getting 50% output as the input, right? So this was the complete simulation on single phase full bridge inverter using square pulses, right? So if you have any doubt, if you want to give suggestions, you can tell me in the comment section, right? I'll try to reply all of you. If you want any other converter to be simulated on MATLAB, so please do let me know. I'll try my best, right? So for now, take care. Thank you. Bye bye.